So Stefania, sorry, is an astrophysicist working at the ESCAPE project, which is the European Science Cluster of Astronomy and Particle Physics for ESFRI research infrastructures, working as a scientific support postdoc at the Observatoire Astronomique de Strasbourg. And she's also worked as a research associate in the Cornell Center for Astrophysics and Planetary Science. And she did her PhD at the Observatoire de Paris in 2018 with a thesis on the star populations and scaling relations of galaxy clusters from the first epoch of assembly to the present. And she got her master's degree at the University of Bologna, and she's based currently in Strasbourg. So Stefania, the floor is yours, and please correct me if I got anything wrong.
Okay, no, that was all perfect. Thank you very much for this very nice introduction. And thank you all the organizers for this wonderful workshops. So I'm here to talk about the ESCAPE project. As you said, ESCAPE is a European funded project by the Horizon 2020 program, and it started in 2019 and will continue through January 2023. So as you said, ESCAPE stands for European Science Cluster of Astronomy and Particle Physics, ESFRI, which is an acronym for the European Strategy Forum of Research Infrastructure. And you can see here a nice map of all the research infrastructures involved from the astrophysics, particle and astroparticle and particle physics community. So the aim of the project is to bring together different communities to address the challenges of open science, open access, and the long-term usability of multi-wavelength and multi-messenger data. This is the idea that stands behind this European Open Science project is to connect on a wider environment that is the European Open Science Cloud, which would be a wider, is actually a wider multidisciplinary ecosystem, which includes not only the astronomy community with ESCAPE, but also life science, environmental science, social science communities, and that wants to build a large web of fair data and services. As we heard in these days, we as astronomy community are already have done already a lot of work towards the open science. So we are a very important building block of this European Open Science Cloud. I'm showing here the work packages that are involved within ESCAPE. I'll list them quickly, and then you have some more details here for completeness. So ESCAPE is made of 5 main working packages. We have a group working on the software repository, on the data infrastructure, the making up of a science analysis platform, and also a working group for citizen science projects. For this talk, I will in particular focus on the ESCAPE virtual observatory activities, which is the group where I'm mainly involved in. So for the virtual observatory, our work is to extend the interoperability standards that we already use, and we have a very important synergy here with the IVOA, and to bring these standards to a broader scientific context, and also prepare the virtual observatory to manage and interface with the large volume of data that the research infrastructure partner research infrastructure will bring in the near future. In more details, the work that we are doing, the activities that we are involved in, have the are driven by these three main objectives. So the first one is to integrate the VO data and services in the European Open Science Cloud, bringing englobing the VO registry of services into the ESC framework and participating into the Research Data Alliance. Then implement the FAIR principle in astronomy, and we'll see some examples in a while, by bringing the common standards for interoperability that responds to the need of the researchers, support the science community, and we've had 2 training schools in 2021 and 2022 that were held virtually on the topic of science with interoperable data. And I'll share after some resources that we've prepared for the schools and that are that can be accessed even, I mean, that are public, can be accessed on the web. We've hosted a technology forum event to prepare the European input for the International VO Alliance, and also hands-on workshop for the data providers about the publication of data using the VO standards. And lastly, another high-level objective is to add value to the scientific content of the archives, or the astronomical archives. And I'll bring here as an example the work that has been led by our ESO colleague about using deep learning to add value to the archives of spectra. And in particular, there's this paper by Sedegar et al. That's about using deep learning to infer the stellar parameters, just analyzing the spectra in the ESO archive. So you can check the reference here. I was talking about the standards, and there are two recent ones for the IVOA that were led or contributed by the ESCAPE partner, and we have the provenance data model that is a standard now finalized and approved in 2020 that propose a model to describe all the information that are related to the publication of the data. And the second one, which is more recent, that has been approved by the IVOA in March 2022, that is about the multi-order coverage map version 2.0, that I will provide a demo on this in a few minutes. And so MOC is a very practical and efficient way to describe complex regions of the sky, and in particular the second version includes has been enhanced with describing both space and time coverage simultaneously. And this particular enhancement of the MOC was driven by the needs of some of the S3 like EGO, ESO, and our radio astronomy partners, in particular to be able to describe, to provide sky coverage map for the detection of gravitational waves. I will now move to a short demo of how we can use FAIR data with the multi-order coverage map. You can find this at this link that I forgot to share with you, but I can do this now. Sorry, I wanted to do this before, but I forgot. Okay, I'll copy paste it on Slack. So this is in Binder, and it's called MOCPy tutorial Rosa 2022. So what I suggest is that you can either follow with the link that I sent you, or follow me during this demo. So in the interest of time, I have my notebook here that is already run, because I've noticed that there were some connection problem in the live demos before. Okay, so I'd like to, please let me know if you don't see the notebook in my shared screen. Otherwise, I assume that
we can see it, Stefania.
Okay, that's perfect. Okay, so as I said, the MOC is a standard of the IVOA that describes arbitrary sky regions. And this is based on the HELPIC sky tessellation, and is particularly useful to describe the footprints of surveys, specifically for regions that are not regular but are arbitrary polygons from that we can derive either by putting together different images from a survey or a list of sky coordinates. And this could be created either from images or data catalog tables, and are very efficient in performing logical operations like intersecting, summing up, computing the difference of the complement of different maps. And as I said, and I hope that I'll have time to show some also application for the describing space and time coverages. Okay, so you can follow the link to get the MockPy's documentation. So this is the MockPy. This notebook uses the MockPy package that implements this the mock technology, and I'll use also AstroQuery, as we've seen before, and PyVO to find and access data, then MockPy to work with the mocks, and also other AstroPy functions, useful functions. And then to visualize the maps, I will use either this word to screen function from MockPy, or also other possibilities are, of course, Matplotlib, and for an interactive visualization, the Aladdin widget for IPython. That's called IPy Aladdin. Okay, so to have a look at a useful application, we can start by querying the mock servers hosted at the CDS to get dataset of our interest. For this, we need to know, we need to look for the metadata identification. So to start with something simple, here I'm using the CDS AstroQuery function to find the datasets that have in their ID SDSS and XMM. This is the result. So we have different bands for DSS and different options also for XMM. So once that we've chosen the ID that we want to access, we can specify in the metadata keyword this ID, and we can query for the mock. So, for example, in the case of DSS, we will visualize it in a bit. We can we here are accessing the union of all the maps found in the CDS server, and in the same way also for this other data set. So once that we have, I remind you that the mock described the coverage, the footprint of a survey. So this is very useful to answer questions like, I have a given source. I want to quickly find if this is observed by a specific survey. So what I need is the coordinates of the source. So either I already know the coordinates, or I can query the SIMBAD, which is a reference database for astronomical sources. So I can use the name of the source and find the coordinates, and then I can, with a simple line code, ask if this mock, for example, the maps describing the spatial coverage of XMM contains this set of these locations, and I have that this is the case. Then I can compute the intersection, and this is again another simple line of code. I just write here, I want the intersection of SDSS with XMM, and I save everything in a new array, in a new mock. And for example, I can compute the sky fraction that is covered by the two surveys, and save everything into a FITS file. Now, to visualize everything, I have here an example, as an example, Aladdin. So I can use IPy Aladdin to have this sky view with a given survey. And I've already done this. It's usually fast, but I prefer to do this in advance to just use Aladdin to plot the mock. So and I can interact with this window by having here the two surveys or the intersection of the two. Another interesting feature would be to filter at a catalog by a mock. Like I have a catalog of sources. Can I select those observed by both? So I've gone quickly through this step, but you can later follow the notebook to see how can find a catalog, access the interesting data, and then compute the sources that belongs to the intersection. And if you want, also plot visualize the sources within the same plot. For the space and time coverage, I've followed here basically the same approach. I'm using here PyVio and the Table Access Protocol service to access a catalog. So I'm looking for the Quasar catalog in SDSS. So I find here the catalog I'm interested in. I take the name of the table that I want to query, and then what I'm interested in this time is to access the location of the sources, but also the time they were observed. So we have this table here with bonafide Julian date, and so I query the catalog with these three columns that I'm interested in, and I define the times and the longitudes and latitudes. And here I create with stmock, which is another module of the mockpy, and I can create a spatial and time coverage using the times and the position. So there's a simple syntax. And I know here that I have observations between 2000 and 2016. And with looks complicated, but it's not really complicated. I can decide the time ranges that I want to select and plot and also get the data separated by the time ranges that I'm interested in. So I'm quite done, and of course I can do the same operation that I've done before, taking another survey, computing the same, and then so I'm doing the same thing with another survey here. And I can answer questions like, what are the sources that are observed at the same time with these two surveys or more surveys? So I can compute the intersection of space and time. So that's it. It was pretty fast, but I hope it gave you an overview of what can be done with mocks. You can discover all the functionalities on mockpy with more tutorials. And that's also, as I anticipated before, this was used to describe or to plan the multi-messenger observations, like follow-up observations of gravitational wave events. And there's a very interesting paper by Greco et al. That it's published in Astronomy and Computing. And there's a related notebook that also reproduces the content of the paper. So I stop here. I'll share the slide with all the links that I've talked to you about. And yeah, I'll end up here. Thank you very much.
No, thank you, Stefania. Very interesting. I see a number of links also appearing in the chat, but we don't have any questions. Well, we don't have any. How much? So there is this association of observatories from the optical to the radio. You've mentioned the provenance data model. The provenance data model is more a tool for recording provenance. So there are ways you can still use the standard, but not have interoperable provenance. Have you been working, or is the Escapees project working on that, so that the provenance information can be more easily standardized across observatories?
Probably since the provenance data model is a quite technical model, I'm probably not the best person to report.
Sorry to put you on the spot.
On this, but yes, the discussion is. So the work of Escape is to talk to the different communities and understand what are the what they need as and try to connect these. I cannot report on how difficult.
Okay, sorry. I'm just happened to be very interested in the provenance data model when I was working with the IVA, and you mentioned it, so it's my fault, really. No worries about that.
No, that's, yeah.
Any other questions? I don't see any on the chat. If not, let's thank Stefania for keeping to the. I see Janet Evans is typing something.